This is the sulfur sp3 orbitals. So did you guys figure out how to fill them with 6 electrons? Did anybody figure it out? I know John Carlo figured it out, but did somebody else figure it out? Is this right? This can't be right. Absolutely cannot be right, because this would show 2 lone pairs on sulfur. It can't be. Sulfur only has 1 lone pair, but it has 6 electrons. So did somebody figure it out? Where does the 6th electron go? To the d orbital? Yeah, to the d orbital. That's correct. This one goes to the d orbital. Why not a p orbital? Why can't I just put the 6th electron into a p orbital? Yeah, there's no more. We used all 3 p orbitals for the hybridization here. There are no empty p orbitals left. There's 0 unhybridized p orbitals in sp3, and therefore we have to go to the next available, which would be the s, but the s is a 4s, let's say, for sulfur. The 4s versus 3d, so we're going to go up to the 3d. All right, and then this is where our pi bond comes in. We're going to have an oxygen sp2 come in here. And so there's going to be an sp2 sigma bond here. It's a sigma. And then there's going to be something of a p. You know, when we have a multiple bond, it's going to be a sigma and a pi bond. And it's going to be a pd pi bond. And so let's talk about PD pi bonds. I haven't talked about that yet. What a PD pi bond looks like is like this. A p orbital's, this is our standard p orbital. A d orbital can pi bond also. A d orbital is going to look like this. It's going to have the 4-leaf clover type shape. This. And so this would be a d orbital. One d orbital. And so we have, we only can overlap half of the d orbital here. We can only overlap these 2 lobes. These 2 lobes are just free and overlap. So this would be the side view. Let's try to draw this by a top view. Picture of this. Let's do it over here. And so a top view would look something like this, where we'd have the p orbital here, 1 p orbital lobe coming out, this one going in, this would be our p, and then we'd have our d here. And now our d, 1 lobe is going to come out, another lobe is going to go in, and then 1 lobe comes out like this, and another lobe goes in. So this would be the d. And so all we're trying to do is we're trying to take this one and tilt it on its side, 90 degrees. Can you see that? Now, how do we draw this in sulfur? Well, I just tried the best we can for this. So let me just erase this temporarily here. And so this one's going to have sulfur here. And then we'll put an sp3 up here. So we got the sp3 and then the oxygen here. Oxygen's sp2. So we'll just do the sp2s like this. so here is our sp3, sp2 sigma bond. Now we have to draw the pi bond. And this is going to be a top view. Can you see it's going to be a top view because of the orientation of the sp2s, or trigonal planar. And so if we're looking at it from a top view, then the p orbital, unhybridized p orbital on oxygen, sticks straight in like this. And so this would be the unhybridized p orbital, which we have 1. And so that means we have to draw the d orbital on sulfur. Well, the d orbital, we have some liberty if we're drawing this. We're just going to draw like this. There's one lobe coming out. This is going to overlap with the P, the lobe sticking out. And there's one D lobe going in and down. And this is going to overlap with this P lobe down there. And so this is showing the sigma and the pi bond here. And as far as the electrons go, we'd have one electron from the oxygen, P, and one electron from the sulfur, D, like this. Now there are 2 more lobes. These other 2 lobes aren't going to participate here. So there's one sticking out here and one going in here. And so this is what we'd call the top view for this, or what I would call the top view. And then we would do the side view as well. The side view is going to look like this. We'll take this one and tilt it on its side. So if we take this one and tilt it on its side, we're going to have the oxygen, and we're going to put the p orbital in profile now, because the p orbital is going to come into the plane of the board. Like this. And that means the sp2s are now, well, one sp2 is still in the plane, but these other 2, one's going to stick out like this, and then one's going to stick in like this. sp2 here and sp2 here. These sp2s will have lone pairs. Then on sulfur, we would have the d orbitals here. Well, sulfur is going to be having this sp3 here. And then we'll just draw the d orbitals like this. The d orbitals are like this 4-leaf clover type arrangement here. And so we'll see, what we're going to see here is we're going to see the pi bond right here. Well, we have the p orbital with 1 electron, the d orbital with 1 electron. And so this would be a p-d pi bond here on the side view. Okay, do you see that? Now, what we're going to do is we're going to draw on the rest of the sp3 orbitals on sulfur here. So it could get messy. And so one sp3 orbital is in the plane, so we got 2 in the plane, and then 1 coming out, sp3, and 1 going in. And then we have a lone pair. Maybe what we'll do is we'll put the lone pair in the orbital in the back here. And then we have oxygen, sp3. Here. And on oxygen, sp3, we'll put 2 in the plane. This. 1 coming out, 1 going in. Okay, now this sp3 will bond to the hydrogen here, S. Hydrogen S. So 2 lone pairs. Fill in the electrons here. We'll do another one here. Keep it kind of symmetric like that. Now, the hydrogen S And the oxygen, this bond doesn't have to be in the plane. There's free rotation around the sigma bond, so this can rotate out of the plane. But we'll just freeze it in this is called a conformation here. There's no free rotation around the multiple bond, however. But did you see how we did the d orbital, threw it in there? Normally we'd have a pp pi bond, but this is unusual in the sense that we have a pd pi bond. So PD pi bonds are available when d orbitals are accessible, like n equals 3, n equals 4, n equals 5. You know, we have d orbitals accessible. N equals 2, we aren't going to do this. So the question comes up, should we expand the octet or not? So let's take a look at sulfuric acid then. This is sulfuric acid. Now sulfuric acid, there are two structures that we can generate. Can I erase this? Now, I'm going to talk about advanced, so since we're doing sulfuric acid here, and sulfuric acid is a bit advanced, we're going to talk about the bonding here. Let's compare the two here. If I look at let's call this oxygen A sulfur bond. If I look at the oxygen A sulfur bond, what do I see? I see an sp3 sigma bond, right? And so sulfur to oxygen A, we have an sp3 sigma bond. You did earlier. But when we have a charge like this, negative and positive, you know what that looks like? We've seen that before. So for example, let me do this quick aside here. If I did the sodium chloride Lewis structure, a sodium chloride Lewis structure looks quite a bit different because it has ionic bonding. And so we have the sodium ion and the chloride ion. And the ionic bond is the attraction between the oppositely charged atoms, right? That's an ionic bond. Well, not only do we have the sp3 sigma bond, but we also have, because of the sulfur is positive and the oxygen's negative. If the sulfur is positive, the oxygen's negative, then we also have an ionic bond. As we have oppositely charged atoms, those oppositely charged atoms are going to attract each other by ionic bonding. Okay. All right, versus this. If we were to expand the octet, what we're going to just have is this. Well, one bond is going to be the sp3, sp2 sigma. And the second bond here is going to be the not P on sulfur, D on sulfur, P on oxygen, pi bond. And so the primary difference is both of these will have a sigma bond. But what is it? Is the bond going to be more ionic, or is the bond going to be more covalent, as in the pi bond here, the PDP pi bond?
Well, it turns out that in the past, what we would say is if you can expand the octet, that is, skip out of this. If you can expand the octet, then do it. Because minimizing formal charge is important. But at the end of chapter 11, there are some unresolved issues. The unresolved issues is this. Recent calculations, recent quantum mechanical calculations, and normally this is, when you look at the structure, in fact, if you go to Wikipedia, let's go to Wikipedia and look at the structure for sulfurous acid. Let's take a look. SO3. What did they do? They did a double bond. Double bond. Do you see? Double bond, this has always been the case. We've always double bonded this. And this has always been known as a PD pi bond. PD pi bond here. And we minimize the formal charge. This whole controversial thing that came up recently, and that is, what is the percent ionic character in this bond? And some recent calculations have shown that the percent ionic character is higher than what was originally thought. In fact, the contribution of d orbitals, like in SF6, let's go to SF6 for a moment here. If we look at SF6, then what's the hybridization of sulfur in SF6? Well, I'd say this is sp3d2 hybridized. And so each orbital consists of 1 part S, 3 parts P, and 2 parts D. And so what is the percent D character in this orbital? We could figure out the percent D character by, it's 2 parts D, right? So let's do that up here. It's 2 parts D for how many total parts? It's 6 total parts. Times 100. And so it's 1/3. In other words, it would be 33.3% D character in this orbital. And so we'd have to blend in a lot of D orbital in there. Well, recent quantum mechanical calculations have shown that the percent D character in this orbital is close to 0. If the percent D character is close to 0, then how do you bond it without having those extra 2 orbitals? Well, this is the proposal that came up. The proposal that came up is sulfur does not expand its octet. Sulfur maintains its octet. And so if sulfur maintains its octet, it's going to form a maximum of 4 bonds here in an octet.
Well, how do you fit the extra fluorines in there? Well, the extra fluorines is thought to come as an ionic bond. And so if you do this here, you end up with a +2 charge on the sulfur, formal charge, and then you have 2 fluoride ions. And so the extra 2 fluorides would be ionically bound. But when we look at all the bonds are all the same, exactly the same. If all the bonds are exactly the same, then how can we have 4 covalent and 2 ionic bonds? Well, what they came up with is this. They came up with that they're going to be resonance forms, you know, where the position of the ionic bonds are. And so here the 2 ionic bonds are opposite. Here they're adjacent. And then we have different positions. So we just pick all the different combinations of this, where we can position the ionic bonds. And then once we have all the contributing, these are resonance forms for ionic bonds. Normally we don't do resonance forms for ionic bonds, we just do resonance for multiple bonds. But this is the same type of concept. And so there would be more structures here. And then when we combine all of the structures, then we get the resonance hybrid. The resonance hybrid would show that each of these is part ionic and part covalent. In fact, when we look at this, if we have 2 out of the 6 bonds are ionic, then that means it's 33.3% ionic character, 66.7% covalent character in each bond, and all the bonds are equivalent. And so this is one way of doing it without ever having to expand the octet. And so, since expansion of the octet, or forming multiple bonds here, and expanding octet require participation of d orbitals as hybrids or as unhybridized. This is an unhybridized d orbital that we had. Oh, where was it? Over here. This is unhybridized d orbital. That's a hybridized, but it doesn't matter. They're saying that there's not that much d orbital participation in this. And so that and so are they saying hyperconjugation is this, this mixing in of ionic bonding in here. Hypervalent is just keeping everything covalent and then just expanding octet. And so they're asking, okay, should we keep an octet and then introduce ionic bonding, or should we just keep it expanded octet? And so when they compare to the quantum mechanical calculations, they look at the charge on the atoms there. And the end result is, you don't have to worry about this, the end result is expanded octets is questionable, since wave function calculations show very little contribution from d orbitals. And so the reality is this. The electron density is like water; it's just going to spread out. And if it can go into some of the D, then it would. And so, how are we going to handle this? How we're going to handle this is we might try just drawing 2 structures. And so for sulfuric acid, we draw the structure with an octet of an ionic contribution and an expanded octet. And then what we do is we say the true structure lies somewhere between these 2. Because what it said here is this. Very little contribution. Very little means 0? No. It means that there is some percent contribution, maybe not 33% contribution, maybe something less. Well, if that's the case, then what we do is this. We just say that the actual structure is a hybrid of these. And it might not be an even hybrid. That is, it might not be a 50-50 hybrid, but some hybrid of this. And the hybrid would be biased towards the more stable structure. Hybrid biased towards more stable contributor. We saw something like this before, where we didn't have like a 50-50 hybrid.
we bias the hybrid towards the more stable structure. Do you recall what molecule that was? In which it wasn't. For example, in acetate, it's easy. It's -1/2 and -1/2 on each oxygen in the bonds because it's a 50-50 mix of those two. But in this particular example, it wasn't a 50-50 mix. And in fact, I made an 80-20 mix just by guessing that one structure was maybe 80% more stable than the other. So that structure should contribute more to the hybrid. Do you recall what structure that was? I'm sorry? Which one?
Butyric acid?
No, not butyric acid. That wasn't it. Well, you can just check to see if that's in your notes. If it's not in your notes, ask me tomorrow about it, but take a look and make sure you have that and you understand what's going on with that. But anyway, this is the structure for H2SO4 from Wikipedia. When you look at this structure, what do you see? I see the sulfur is going to be what hybridization? sp3. And then I see two double bonds. Each double bond is going to consist of a sigma and a pi bond. And so if sulfur is sp3, then this would be an sp3. The oxygen, even though they don't show lone pairs, That's a problem. When you get to organic chemistry, oftentimes you leave off the lone pairs because you automatically know. But since we're in general chemistry, we got to write them in there. Otherwise, we don't assume that you already know. And so how many lone pairs on this oxygen? Two, and this would be what hybridization? sp2, so it would be an unhybridized P. And so it would be a P pi bond? This has got to be a PD. And then this one must be a PD. We're going to form two PD pi bonds. Now, if we form two PD pi bonds, where are the d orbitals? So I have a clover leaf here. Where's the other clover leaf? At what angle? All the d orbitals are at 90-degree angles. If all the d orbitals are at 90-degree angles, then if we're using two of them, then we have one here, and then we've got to have one here. But the other d is at a 90-degree angle, but this is tetrahedral, and this would be at a 109 angle. And so do you see the angles are screwed up? If we're using two d orbitals, one d orbital here for this pi bond and one d orbital for this pi bond, then this angle, this bond angle, should be 90 degrees because that's where the d orbitals are. But the bond angle is actually 109. The bond angle is 109, then what happened? Well, that's going to result in pore overlap. In other words, what we have to have is we have to have a different mix, in terms of the hybridization mix. And so, so having one PD pi bond, okay, but having two PD pi bonds might start getting less favorable because of do you see the angle constraint there? Well, we're going to talk about this one next tomorrow, so we'll work on this one.